Hi everyone, welcome to our talk on evolution of observability at Riot Games. Thanks for coming in and let's keep going. So let's start with a little bit of info about us. My name is Kirill, I'm a software engineer at LiveOps at Riot Games, and today with me is Erick. He's also a software engineer at LiveOps organizations. And this is actually our kids. They look surprisingly suspiciously the same, but there's a big reason we're here. So without further ado, let's get started. Let's start with what is Riot Games. Riot Games was founded in 2006 to develop, publish, and support the most player-focused games in the world. Our first game, League of Legends, was released in 2009. League went to become one of the most played PC games in the world, and also becoming a global leader in esports. In 2019, as saying goes, we put the S in Riot Games, releasing Teamfight Tactics, and followed by League of Legends, Wild Rift, Legends of Runeterra, and Valorant in 2020. All of this growth produced a lot of challenges for tech teams to make sure that the games are not only fun to play, but also offer stable, accessible gameplay. This is even more important for non-online competitive games, as they demand increased stability and performance, which is true for esports, with millions of people all around the world following live games through the multiple channels. The same actually goes for LiveOps organizations, and growing portfolio and scope of the games required us to have a wider and wider set of reliability requirements to make sure that the players are having the best experience. So now let's talk about what actually makes observability different at Riot Games. Well, in some cases also in gaming industry in general. So first of all, let's talk about technologies. As Riot Games portfolio grew, the number of platforms and technologies we used grew. Today, Riot Games are being published on Windows, Mac, iOS, Android, PS5, and Xbox. Needless to say, it brings new requirements on how we should differentiate the platform and observe user experiences across all platforms. Riot is a global leader in esports, with millions of people watching games live every day. Esports events require very true attention to make sure that the latency and stability of the services are absolutely impeccable. So the best players in the world could show their talents without any technical difficulties interfering. Games are also getting more complex, with a huge variety of game mechanics and experiences. This requires a large amount of tech to support it. And we operate more than 1,000 traditional backend services written in Java, Go, Python, Erlang, and many others. Of course, we have databases, queues, load balancers, streaming platforms, and many others are also present. But we also want to make sure that the online experience of every single game holds to the same level. While Riot is actively working on decommissioning most of its own physical infrastructure around the world, we still collaborate with our cloud partners to provide the best network and routing infrastructure for our players. So actually, let's dive deep a bit more on the network side of it. Network observability plays a key role in making sure that the players are having a great time. Very few things are as bothersome as stuttering experience during a competitive online match. Ping is not something to worry about too much while browsing web pages, while more than 100 millisecond spike in a game of Valorant will be very troublesome. Also, since the amount of data points is very high due to high frequency of data exchanges between client and the server, not all of the system for observability are suitable. Especially if we're talking about the third-party vendors, we need to have a wide range of instruments to work with the data in our pipeline, including but not limited to aggregation, throttling, sampling, and others, as well as strong requirements to have short delays on our data passing through the pipeline. So this is a pretty good example of the importance of the network and latency measurements. In this image from our official tech blog, linked to the sources and below the image itself, the image shows how far a player who starts fully behind cover is able to peek around the corner before their opponent sees the movement. It's an impressive difference. This is especially highlighted in esports matches, where people play with incredible reaction time. To solve all of these issues with networking, we run games close to our players. We operate more than 100 Kubernetes clusters in more than 30 regions, and we do have publishers to publish our games in some of the regions. All of this makes our journey into observability and SRE in general pretty unique, because as you can see, requirements in gaming may be quite different from traditional observability. So now let's talk about how we're solving actually, and how we solved these problems in the past, and talk about the history of observability in Riot Games before. So early days of observability were characterized by team-specific observability stacks, which may include Zabbix, Graphite, Nagios, Grafana, and many others. Team used to own their own observability pipelines. Shortly after, the telemetry team was formed in order to start building a centralized solution, and Zabbix was chosen as a main tool in observability pipeline. Multiple Zabbix instances were scattered throughout the infrastructure. In order to effectively work with them, a custom API was built in front of the multiple Zabbix instances. And Grafana was used to generate visualizations through this custom API. So here you go, it's probably our first observability pipeline. Along the way, the data team started using Elk Stack as a long-term storage, and they proposed to use Elk Stack for observability also. So Elk Stack started to slowly push out the old Zabbix approach. A custom API was made to support both platforms, so the change went smoothly. The data we pushed to LK stack through an in-house build collector from the services. So this is probably the second generation of our observability pipeline. And we actually found out that Elk Stack was not really easy to maintain for us, and it was not really suitable for our use cases regarding real-time data at the moment. And we end up swapping it with a third-party vendor, which was used as a replacement for Grafana and Elk Stack. So this is our next iteration of observability pipeline we end up with, but there were some problems with it. So now let's talk a bit more about the problems we encountered. So first of all, it was hard to integrate. We developed the last iteration with our common frameworks in mind. It was very easy to integrate, but everything outside of Golden Path required a lot of effort, since it required a lot of manual work to get basic telemetry. It was hard to deploy on a large scale, since the number of services was and still very high. At the same time, it was slow to adapt. Large part of the system was still in-house built. Because of the adding any new emerging technology would require a lot of time and effort from the team. And it's mostly caused observability pipelines, to be easy to bypass, or in other words, governance was difficult. As an artifact of an early days where teams had separate pipelines for observability, for some teams it was just easier to bypass the pipeline overall. It's just easier to build their own way to push data, as an API keys was pretty freely available. It produced a lot of issues for us with the cost associated, since we used a third-party vendor to store and query data, as well as it kind of produced a different triage experiences for the teams. Expanding on the last topic, let's talk a bit more about fragmentation and cost. We had pretty huge issues with observability and the fragmentation of it. So the first issue was standards. Different sets of standards across teams on telemetry data. We had different metric name, tag, service catalog setups. Observability and infrastructure as code was defined separately per team, making it pretty difficult to amend if needed for operators. With growing number of services, triage was also harder to do. We see traces as one of the ways to solve it, but there were no supported at the time. There were no unified libraries, unified approaches to it, so every team was on their own. Another artifact of early day was that when we had separate pipelines, every team or group of teams had a separate account to query data, which made cross-team triage excessively hard. And the same goes for actually code access. Each team managed their own repository for their infrastructure as a code and had their own CI/CD pipelines for monitors, dashboards, etc. Another issue is wastage. Wastage was hard to control. With fragmentation and not a single point for telemetry ingestion, it was easy for teams to explore, but hard for us to control and turn off the tap. And a bit of data. A single metric accounted for 150 terabytes a month of data ingested that were never queried. A single load test generated over a petabyte of logs in a single weekend running. And one of the interesting one, lack of standards actually caused some teams to adopt using variables and metric names. So there were a lot of unique metric names, and the wastage was hard to pin down. So they were basically wildcarding the metric names instead of using tags. And to summarize it up with one single number, we were ingesting 3.5 petabytes of data monthly. And it was growing, and we had a lot more stats towards it. We had like a 300 million synthetics runs, and all of this cost us to solve a new way to approach it. And I'm giving it up to Erick to talk about like a new approach.
Thanks, Kirill. So let's talk about. Is this on? Okay, it's on. Thanks, Kirill. So let's talk about the new approach and how did we went on solving some of those problems. This is going to be a very condensed version of what exactly happened. There's like a lot of talks out there that goes into details, like talk with similar stuff, but it should give you an idea. So what we changed and how we changed, right? But first, we have to talk a very important thing that's we switched vendors. While this is not fully required, and we totally understand that, but this has many implications. So one of them, it's allow us to control and gatekeep bad practices as we start seeing them. It also gives excitement for the teams and a timeline for everybody to move. And one of the things you can use as well is most of those vendors will offer a signing deal. Like it's going to grow over time, but you can use that to fund your projects. So, but yeah, this is very important. We have to say this up front, but let's go to the tech stack. So the first thing we introduced was a new telemetry pipeline in replacement for our older collector in-house. For this, we decided to go with Vector, although another common option out there is OpenTelemetry Collector. But Vector had everything you needed at the time, and a good set of sinks and transformations, things like the duping, throttling, sampling, buffering, and like back pressure and more. It has good performance, it's written in Rust, it performs 3 times faster than our old collector in load test. It's open source, mature community, good documentation, as usual. And it's easy to develop and has great built-in tools such as querying APIs, auto-reloading, tapping, graphing, like way more. And specific about this point, here's a screenshot for a tool that we're developing internally. It's not on the wild yet, but you can see a little bit of our pipeline in the middle. So this is a debugging tool. Like we have a quite big pipeline at this moment. So you can see a little bit of the pipeline in the middle, the transformation code in the left, and some of the events flowing and some select transformations on the right. So this is an example, but people are building similar stuff. Even Datadog has some stuff also built on top of Vector that you can use. The second piece of tech, we deployed, well, the Datadog agents on our clusters. There are some open source alternatives. We've seen these from Grafana, for example, yesterday. And well, what those agents do, and probably very tired of hearing this all the time, is they extract all the CPU and memories, CPU and memory metrics, and using eBPF also extracts network information. With the network metrics, it provides us the ability to visualize all the service map, like with zero effort also to monitor all the HTTP requests. You can scrape Prometheus endpoints, collect traces, and send all things to Vector. It supports all environments we have. It's specific about Datadog agents. It supports all Mesos, EC2, Fargates, and Lambda, so all the other environments we also have. The last piece of major tech we introduced, a little bit more bespoke. This is maintained by us, is dynamic admission control webhook. I have to read from here because I keep messing this myself. So what it does, it injects annotations, attributes, and vendor-specific configurations. So service teams don't need to know about what vendor you're using. It allows to create our own interface of annotations and attributes. So this allows to swap tech and versions behind the scenes. And also allow us to provide same defaults for things like Prometheus configurations. So it's also able to intercept and modify the pods to inject things like APMs or open source APMs, vendor APMs, whatever. So the teams never actually specify, I want Datadog APM or anything like that. We do that for them. And some specifics of the pipeline, we also introduced sampling, where actually we're just out of another talk earlier today from Udemy, that you can get more into the details on why this is important. But the way we introduce a Riot, warn logs, for example, are sampled at 10%, info at 1. We have some other specific configurations for different severities. Traces are dynamically sampled according to service usage. So the service that's using more, it's going to get sampled more. The service that's using less is going to get sampled less. Also, with errors, it usually skips this process. And teams can opt out instead of opt-in. So this allows us to have the conversation with the teams before like they actually start pushing stuff. And this can be fine-tuned by service, region, environment, and all configured and remotely synced to our collector instances. So here's an example. So you can see our Canary applications on the left. In the middle, you can see the regions, and on the right, you can see the severity and the sample rate. Everything is set to 1 because those are our Canary applications. We need their logs to go through to do Canary stuff, but we do have other ways to test the actual sample rate. In similar fashion, we also introduced the gatekeeping for metrics. So no more pushing metrics directly to Datadog. This is to counter what we mentioned previously. So about tag cardinality and metric names with labels in them. Metrics are mostly allow lists, but there are exceptions. So things like queues, database, internal frameworks get this keep. And allow lists are also stored dynamically using GitHubs and our changes synced remotely to our instances. So this wouldn't be a tech talk with no tech overview. So here's a little bit of the diagram of the whole flow. So a K8s resource gets pushed to our clusters, gets picked by the webhook, it gets modified, pushed back to the cluster, then the service gets deployed, the agent reads all those attributes and annotations, extracts the telemetry. Both of them send data to vector, mostly the agents doing the heavy lift, but sometimes there is some exceptions, servers have to send telemetry as well. The configuration is updated remotely, things like sampling and allow lists. And then it pushed to Datadog. And it also, during the migration, used to push to our old collector and old vendor, but this is mostly gone right now, so it's just to Datadog at the moment. It's also important to talk about a few additional changes we did. So one thing we do is we encourage all the teams to move all the Terraform files to a single monorepo. This allows us to push templates, apply policy tags, change the metric that you're using behind not without, but with their approval, but like applying for all the service at the same time. We also apply data corrections and vendor-specific attributes, so we extract tags from metric names now. We filter high cardinality tags, we normalize environment names, and we also inject specific attributes for vendors, like Datadog has a set of attributes that they expect, or they work better with, let's say. We also introduced tighter controls on API keys and vendor functionality, so API keys are limited and approved only when necessary, so this blocks the bypass we had before. And vendor-specific tag is vetted and tracked by us and to ensure governance and compliance. So no more 3 million synthetics running without us knowing. And we also have a robust CI/CD for this whole pipeline. So we have hundreds of unit tests, integration tests, Canary applications, as we said, constant load tests, A/B deployments, automatic promotions. Like we went a little bit far and beyond to ensure the telemetry should almost never go down because otherwise it takes all the observability with it. So with the tech part covered, how did we manage to migrate all the teams and 1,000 services under a year? Well, I like to say tech is easy, but working with people is hard. So we had two approaches. It's not a clear cut, so it goes in between and forth. So the first one was what we call white glove migration. It mainly consists of 5 to 20 engineers from live operations embedded in specific teams with high impact services. So you can imagine things like League of Legends, Valorant, central platform teams. This helped us get a deeper insight and cover new use cases that we didn't plan for. This is such a big project that we couldn't foresee everything that we end up seeing. Most of the work was carried by us. The scope of the work changed a lot from team to team. It kept changing, and actually this caused some frustration among some team members. PRs were like getting some time to get reviewed by service teams. And we started noticing as well that the teams got code feet because they acquired little knowledge on dashboards, monitors, that they were not confident with the new vendor. So eventually, we started expanding our approach to self-servicing. It's pretty straightforward. So all the services were responsible to migrate for themselves. But we had put a lot of work on documentation, examples, how things work within Riot, how to connect frameworks to this new approach. We had an on-call rotation with SLA for PR reviews and Slack channels. So I was answering and not trying to go over 4 hours without answering, especially because we're multi-region. It required switching to white glove. As I said, it's not a clear cut, so it goes back and forth and back, like as we start uncovering new use cases through those Ask channels. But the teams were way more confident to migrate over to Datadog because now they acquired the knowledge on monitors and dashboards, and actually they expanded even our knowledge on the technology. So, well, with the big aspects of the migration coverage, I hope it is not too condensed, but with that coverage, we need to talk a little bit about the learnings and the key results we got out of this migration. I think the first thing to say, and I've seen it is quite a common topic here in this conference, sampling. So initially our stance was too aggressive, so we are sampling like at very aggressive rates everywhere, like without discrimination. So we had to ease those requirements. We had to come up with quotas. We had to work with the teams to optimize logs, the source. So like it's the best way to sample is usually at the source because you can be smart about it. You can just keep some log that you don't care or debug information. Second thing we learned is gatekeeping is complicated. The initial process was very manual and lengthy, and we had to improve the developer experience over time, again, with things like quotas, auto-approvals for PRs, this whole sync remotely with GitOps. Vendor locking, but not in the sense that we introduced the vendor locking, but that the teams were using a lot of vendor locking, vendor libraries and data structures. And as we still have the vendor tag, but this is mostly transparent for the developers. They don't see that we're using or that they're referencing Datadog. It's out of their code bases. We are relying more on OpenTelemetry whenever we have to put things on code base. Waste control is a constant battle. So now we have tools to control waste and allow us to have conversations with the teams and bring data about costs. We can gatekeep bad practices before and after they become a problem, but we try not to fully block without talking to them, but we have the tools to do so. Right tool for the right job. We generate a lot of data, as we've seen. Not all required to be real time. Some of them can be logs instead of metrics. Some of them can be metrics instead of logs. Some can need only to be pushed when there is an interesting event. So, for example, if you're always pushing 0, like you can assume 0 on the platform and only push when you have an actually interesting event happening. And serious documentation is actually very, very important. Backlinks, reference, examples, everything like this really sped up the migration and we couldn't achieve without documentation. And lastly, but not least, some of the key results for this migration. So I guess everybody is eager to see the cost reduction. So the first thing is costs. We achieved 30% of cost reduction compared to our vendor bills in the same period for the last year or 2 years before. And we also achieved 5 million in cost avoidance. That is the projected growth if we didn't do anything. We're also using much more extensively the vendor capacities. We finished the project in less than 1 year. And we heard some people actually lost money on bets that we wouldn't finish in 1 year. We are down only to 350 terabytes of logs per month, down from a few petabytes and petabytes on load tests. We dropped 90% of custom metric ingestion with more 6% coming. And we are down only to 300,000 synthetic runs from 3 million we were doing before. Because now we're using more logs and more metrics than we were using. Tracing is widely used, so by injecting APMs and things automatically for most of the service, with some exceptions, we get trace everywhere. So this gives us a clear picture of the player journey and without any deep knowledge on the domain services. Also help drive down the MTTD and accuracy of first escalation because now we know who we have to page, or we're working on that, but now we have the tools for that. With 1 year of operation, we had less than a handful of major incidents with this pipeline, mostly in the beginning when we're still developing the CI/CD. And at a high peak, it can scale to 2,000 cores and 3 terabytes of memory to handle the load we have in Riot. And the pipeline supports all industry and internal formats. We support all the major languages, all major platforms. We have zero reliance on shared frameworks, long gone shared frameworks with telemetry stats embedded in them. So yeah, this concludes our talk. It was very condensed. Again, we'd like to talk more in depth about some of these. Some of those should be their own talks, as we've seen from Udemy, talking about sampling and other things. But we don't want to keep you here forever. Hopefully, this gives you a nice picture and food for thought for your own projects. And yeah, we'd like to use these last minutes to open for questions. And thank you all for listening to us.